So, this is our second webinar of Control Theory Bootcamp. So, let's start this session. So, in previous sessions, you learned some basics of control theory, open loop and closed loop systems, and a bit theory about PID controllers and many terms like transfer functions, etc. So, in this week, you will learn about controllers, more about PID controllers, and an advanced controller, and about MATLAB and Simulink. And in further weeks, you will learn to make self-balancing bot in MATLAB Simulink. And after that, you will learn to control that bot using Simulink only. Okay, so this is our table of content for today's class. So first, we will learn some more about PID controller and then see implementation of PID controller, how it implements in real life. And then I will tell you how we tune a PID controller. And then, as you know, every technology has its own limitations. So PID also has. So I will tell you about that. And then we will move to an advanced controller, LQR. And then I will teach you basics of Simulink. Okay, sounds good. So let's talk about PID controller first. So for this, I will take the example of rocket stabilization. But before that, I have to tell some more about PID controller. So you learn about these things, this proportional gain, this integral gain, and derivative gain. Okay. So this is final equation of PID controller. So you learn about the examples of spring damper system in which you input this ut force vector. So the PID controller gives command by this function. Okay, so this is proportional term and this et term is error here, and this integral term, it's the error which accumulates over time, and this is derivative term. So this is how our PID controller equation looks like and works. So but there is one more equation, this one. This is called discrete equation and it's like this. So can anyone guess why we use this equation instead of this one? So can anyone guess?
Same as last time, you can either put answers in the chat or you can raise your hand and we'll unmute you.
Yes, you are correct. So we get discrete inputs, not continuous inputs, as because our system are digital systems, not analog systems. So you are right. So let's move to our example, rocket stabilization. So you may ask why stabilization is important, why we have to stabilize our rocket. So assume that our rocket is not stabilized and it's deviated by just 1 degree angle. Okay, so for your in kind knowledge, so orbital velocity of a rocket is up to 7.8 kilometer per second. Like this is minimum, it can go more. And if the deviation is for a long time, so like it causes lateral displacement over time. So it causes 1.7 kilometer of lateral displacement in just 1 second. So and it increases fuel usage for path correction and it causes mission failure also. So that's why rocket stabilization is really a big thing. So let's say this is your rocket and you have to go to International Space Station. So there are a lot of problems which you face. So I have to ask one question again. So what do you think, which environmental factor most affects the rocket stability? There are many factors, but I'm asking environmental factors. So can you guess? Can anyone? Mm, Actually, answer is wind. So wind causes lot of trouble in rocket stabilization program. So yeah, wind and atmosphere, right. You are correct. So that's where the PID controller come and it help us to stabilize our rocket. So I will tell you how it does using a simulation. Okay. So uh, so this is our code for rocket stabilization. So I will tell you some basic things. So here, what our problem is, our rocket initial angle is 10 degree and we have to achieve a target angle of 0 degree. Okay. And our rocket is at zero height and we have to go from 0 to 50 and achieve our target angle. Okay. So I will tell you how PID is implemented here. So this is error term, target angle minus current angle. It tells PID like how much error is there. And this integral term, so this is like an iterator and derivative term. As you see in the discrete equation, this derivative term. Okay. And yeah, so let's run the simulation. Okay, so it's taking time. Yeah. Mm. So can you see this simulation page? So this is our rocket and our initial angle is 10 degree and this is graph between angle versus time. So if I launch the rocket without PID controller, so due to wind disturbance, the rocket will go like this. Its the angle will change and it moves, it deviated from their path too much. Okay, so you learn about these terms KP, KI and KD. So I will slowly increase these terms. So first, let's say I put KP to 25 and you learn about this in your last session. So yeah, so it goes like this. So it tries to stabilize the rocket, but it can't because it can't do it alone. So it needs more term, like this derivative term. So if I increase it, let's say to 3. So yeah, it's stabilizing the rocket. As you see here, the angle is decreasing and it's come nearly to 0. Okay, so it's 0.2 degree. So then we introduce one more term, Ki, to take this angle from 0.2 degree to 0 degree. So let's say I put the Ki value to be 40. And then you will see the rocket is also not deviated from the path. Also, and the angle is decreasing. So yeah, it's like this. But you may ask why the rocket didn't achieve perfect 0 degree angle. Instead, I use this Ki term. Okay, so I will tell you like it's why is it. So so it's because we didn't tune it in a systematic way. We didn't tune the rocket in a systematic way. So there are two methods by which we can tune a PID controller. So first one, as you saw, trial and error. I just try by setting Ki and KD to 0 and then I increase KP slowly till the output start oscillating and then I increase Ki and KD. But is this the best method? So yeah, it's not because as you see, I'm not able to achieve perfect 0 degree angle. So here is one more method by which you can tune the PID controller in a more systematic way. So it's Ziegler-Nichols method. So in this also we set Ki and KD to 0 initially and then we increase KP until our system start sustained oscillations. Okay, like not damp oscillation, sustained oscillations, and then this Kp value is called Ku. We introduce a new term and then we put the Ku here in these values. So we get our KP, KU, and KD. Okay, so this is how it works. And this TU terms, so this TU term is like time taken to complete one oscillation. So like it's like that. Okay, so this is all about PID controller tuning. So do you have any doubts till now? So you can ask. Okay, so isn't it? No, this is for PID, which I told this method, and you can use it for PI also and P also. So so actually this is not like it's not relevant for this course right now. You can DM me. I will tell you the whole derivation of this equation and the process like how it derived. So for the time, it's not really that important. Okay. So so next topic, this limitations of PID controller. So let's talk about some limitations. So first is no knowledge of internal state. So I will tell you by an example. Like a blind man is driving a car. Assume a blind man is driving a car and a person is sitting next to him. Okay. And he tells the blind man that you have to go to left, you have to right, just turn 1 meter left, 1 meter right, stop right now. So here, the person who is telling the blind man is our sensors, which PID use, and the blind man is PID. It just doesn't know like the car is skidding, the car is over speeding. It just listen to what the sensor is saying and it's work like that. So its goal is to just achieve the target. So that's it. And second one, as you see now, manual tuning is hard in PID. So yeah, it's it's like tuning a guitar by with just your ears, not any app. And it's like that. So PID tuning is hard if you want to achieve a perfect 0 degree angle. And third one, it can't handle constraint. So let's say the PID gives signal to the motor, like in our self-balancing board, that you have to rotate to 1000 RPM to achieve some desired state. But our motor has constraints, like it can go up to 500 RPM. So our motor can't go to 1000 RPM. But PID doesn't understand that. It just gives the signal, go to 1000 RPM, go. So yeah, this is also one of the limitations. And not adaptability. So like if you're going to make self-balancing board, so if you tune the PID on a flat surface and the bot is working, it's fine. Okay. But if you put that bot on an inclined surface, so what will happen? Because PID is not adaptive, so the bot will not work. Like it falls down because it doesn't like tuned on that surface. So it's hard for like PID can't do this. So these are limitations. So yeah, these are all the limitations of PID. And to overcome these limitations, we have what should we do? So a new controller, we introduce LQR, linear quadratic regulator. So this helps us to overcome these limitations better than PID. Okay. So before going to the next topic, I use the statement that PID doesn't understand state. Okay, but you may ask, what is a state? So let's understand what is a state first, and then I will tell you this term, this thing, state space representation, because it's really important to know before jumping into LQR. Okay, so state. So state is minimal set of variables that tells everything about a system at any given time t. So we can predict what's going to happen next. So did you understand this term, this definition? So for example, Okay, I will give you example. So you know about the spring damper system. I guess you learned this about in your previous session. So there are a lot of terms like spring force and this damper force and this force and many terms. So in spring damper system, there are many terms. So our state variables are position and velocity here. So position by these two variables, you can tell about the spring force, you can tell about the damping force, the overall acceleration of the system. So you just need two variables to explain everything about the system. And we need a minimal set of variables to fit this definition. So it's like that. Okay. So is there any doubt till now? Like any confusion? Okay. So if no doubt, we can move further. So I will tell you why state space representation is important. So this is a equation. These are equations of degree of freedom drone model. So in drone you have two terms like this position, XYZ coordinate, and this roll pitch yaw angles, and this all terms. So these are 12 variables. 12 variables in our 6 degree of freedom drone. Okay. So these are very complex. So like there are many inputs and many outputs in this. So if we try to write this equation for every input and output, it become messy. So like you see this, there are a lot of equation here, and it's hard to solve also. And to understand such control systems, we need a smarter way to organize and analyze all the information. So that's where state space representations come. So yeah, by state space representation, you can represent these 12 equations by just these two equations, just two equations. Here X is this term, these are matrices, and I will tell you what are these in a while. And A, B, C, D are matrices here. So we can represent it like this. So let's go into detail like what is state space equation exactly. Okay. So these are two equations. So this one. So this one is called state vector. So as you all learn in your linear algebra, any set of quantity can be represented as a vector in a space. So here we make a state vector like this. I will show you. So like this. So here x1 is position and x2 is velocity. So this is state vector xt, and this x dot is like derivative. So it's derivative of state vector. So derivative of position and velocity is velocity and acceleration. So it's like that. I will tell you what are these A, B, C, D in matrices, why are they used in a while. And this U is input vector. So like in our spring damper system, as you saw, the input is force. So this is force vector which we use. And then Y is output vector. So in spring damper system, we are interested in knowing the what is position. Okay, position of spring block. So that's why we choose position as output, and this you all know. Okay. So is it clear till now? Any doubts? Okay, so let's move forward. Tell you in I will give you one example so you can understand it in a better way. So but for the time, I will tell you what are these A, B, C, and D matrices. Okay. So A is state matrix. So here is our definitions. So A matrix define how the system current state influence its future state, or you can say derivative of state vector. So this how the state vector changes derivative of state vector. So it's like that. And B matrix tell how the input vector this much, this vector tells how this changes this. And the C matrix define how internal state are converted to measurable output. So I will tell you what's this. And D matrix show direct effect of input on output. So okay, so I think it's hard to understand just by definition. So let's move to an example. This spring damper example. So using Newton's second law, we can write this equation. This mass into acceleration is spring force plus damper force plus the force we applied. And if we rewrite, we get equation like this. And here let's say x1 is our position and x2 is velocity. Okay, x1 is position and x2 is velocity. So we have to write the, so like I'll tell you what we are doing. So this is our state vector and its derivative of state vector. So we have to write this derivative of these two equations, x1 dot and x2 dot. So x1 dot is what? So x1 is our position. So x1 dot is derivative of position, which means velocity. So we put x1 dot t equals to x2 t because x2 is our velocity. Okay, clear till now? And then x2 dot, which is derivative of velocity. It's this term, this equation acceleration. So I use this equation here and then I rewrite it like this. So it's the same equation. I just rewrite it like this. And then these are our A matrix and B matrix. So I will tell you how I put it here. So we put in the first row, we put it like this, coefficient of x1 here and coefficient of x2 here. And then in second row, we put this here and here. So this is how we make our A matrix. And we put this and this coefficient here. So we get our B matrix. So this is how we make our first equation. And for the second equation, we will do similar thing. So y1, we need the output. What? So we need output as a position because in spring damper system, we are interested in position only. Okay. And it's simple. 1 times this x1. X1 is position. So we put it here, 1 here, and then 0 here, and this 0 here. So this is how we derive our second equation of state space representation. Okay, so any doubt till now? So you can ask if any confusion. Okay, so clear till now. Can you guys thumbs up or raise your hand so I can get the idea that it's clear to you? Okay, so I think we can move forward. So this is just a way of representation. Like if you solve these equations, you get this equation. This if you solve this matrix, you get this equation only. So it's just a way of representation. Okay, and this is how we can get the dimension of this matrix. So here our n is what? Number of states. So our number of states is 2. So 2 cross 2. So A matrix should be of 2 cross 2. So yeah, this is how it works. So this is all about state space representation. So I guess you understand the state space representation now. So since we understand the state space representation, so let's talk about LQR. Okay, so in real systems, we don't just want to reach the target, as PID just reach the target irrespective of the state. We also want the efficiency and accuracy. So where this is where LQR comes in, the modern controller. So LQR is like a smart advisor. So you give it different options to control the system, and it evaluates each one. It evaluates each option and then tell you the best possible path. Okay, so that keeps the system stable and doesn't use too much effort. So you can assume LQR is like a Google Maps. So it looks where you are at right now. It means your current state and where you want to be. And he takes many different paths and pick the best one for you, which is best for you and which doesn't take too long or which doesn't cost too much of fuel. So LQR is like that. Optimize करता है process. So I will give you one example. So let's say you are in your parent hostel S6, okay, and you have to go to H15 for some important work. Okay, so here there are four solutions. First, you can go by just walking, or second is you can go by cycle or auto or these taxis. Okay, so these are our four ways by which you can go. And these are Z1, Z2 are possible solutions by which you can go. So for the time, I take four solutions only, and we put these four solutions in a set, and it's called a feasible set. And we give the feasible set to a function. So so why we give it to function? So because we need some way to measure goodness of each of the items in feasible set. So like which one is best for you, best for us. Okay. So this function calculates and then tell you the value, like how much this a particular option will cost you. So for example, if you go by walking, it takes 20 minutes and for cycle 10 minutes, but by walking it costs zero. And let's say it costs 10 rupees because you have to fill your tire also. So let's say 10 rupees, okay. And for auto is 25, for cab is 100, okay. And okay, so I will tell you what is Q and R. So Q and R like okay, so it's like you said how important a particular thing is. So if your work is really urgent, so you put Q to be 10, like it's highly important, and R to be 2, like it's less important for your cost, like whichever for your cost, okay. But is important. Your cost is important, but not that much than time. So you put it like this, and then the function compute the cost. So you get this core cost for these things. So by walking, it costs you 200 units, and by cycle 120, 90 by auto, and 220 by cab. So I guess you got the idea that it cost you less by auto. If you go by auto, it cost you very less. So the LQR tell that you go by auto. So it's the best option for you. So this is how cost function works. Okay. So it's bit technical things. So like this is actual cost function, and this Q terms like is it give penalties. So in actual life it looks like this. So in spring damper system we put two variables, and this term gives penalty to each of the variables. So like in we put position here in the first place and then velocity down. So it tells that penalty give to the position is really high than to the velocity, which is just one, it's 100 times more. So we want accuracy of position to be high. High accuracy we need. And R is like it give penalty to control effort. So like we are we are like giving force as an input, so it give penalty. Okay. So here the penalty is too low, so like you can increase the force. So it's like that. And then we put, and then we put our all terms A, B, and this here, and we get this P matrix. So we don't go into much depth. Just you have to have an idea like how it works. So from here you get P matrix, which is called cost to go matrix, and it tells total future penalty for any given state. And then you put the P matrix here, and then you get this K matrix, and by this you get the control force, like how much force we have to apply to the system. So okay, don't go to that much depth for the time. Okay, so do you have any doubt till now? So you can ask about the theory part, because theory part is over and we are going to jump into practical things. So like if you don't understand any topic, I can repeat also. So you can ask in the chat or okay, if everything is clear till now, we can go forward. So you are, I guess you are right now like this. When will this end? So yeah, it's over. So it's time to do some practical stuffs. So I guess you all received the document of in MATLAB installation. So can you raise hand if you install the MATLAB? Okay. Okay, so you install now, right? Nice, nice, nice. So we will do work simultaneously. So I will tell you about. So we are using Simulink right now. So MATLAB is like a matrix laboratory. Here you can do data analysis and use too much and use you can make simulation things and all that. So MATLAB is for that. And in Simulink, you can like virtually place these objects and make simulations also. And in MATLAB, you have to do coding stuffs in that language. Okay. So, okay. So you open your MATLAB and you see this in this panel. This is the Simulink button. So if you click this, you come to this page and you have to click the blank model to start working on. Okay. So, okay, before jumping to the Simulink directly, I will tell you some basic terms in Simulink. Okay. So this is the sum block. So it likes add and subtract the given signals and give the output of that signals. Okay. And this is gain block. So this is like a multiplication. We can do multiplication in Simulink by this block. Okay. So it multiplies and with a constant value, let's say k, and it gives the output. So it's like a multiplier. And this one is derivative block. This gives the derivative of the function. So like if you put position here, you get velocity. So and it's like that. And this transfer function or integrator function. So if you put like acceleration or velocity, you get velo respective integral of that. And the last one, scope. So scope is like a graph plotter. So you can see that by this how your graph is looking like. Okay. So this is the theory till now. So I request everyone to open your MATLABs so that we can do the Simulink part together. Okay. So guys, those who didn't download the MATLAB, you can search on Google. There is one website which allows you to run MATLAB online also. So you can go there and work with us. Okay. Sounds good. So I will share my screen. So are you guys with me or you need some more time? Did you open your MATLAB? You can raise your hand and tell me. Okay, so let's wait for some more people. Should we start? Okay, so you can open your Simulink from here. And you can create a blank model. Okay. Okay, do you have any doubt? Ryan, do you have any doubt? You raised your hand. Okay, no problem. So guys who didn't download the MATLAB till now, you can search on Google. There is one website which let you run MATLAB online also. Okay, so you can go there also. So guys, are you with me? Did you open this Simulink window? Okay, so let's begin our work. So I will tell you some basic things about Simulink. Like if you double tap here or anywhere, you can get this menu, and from here you can search some every blocks you want, like sum block, gain block, as I told you. Okay. So I will tell you some basic things first. So you can search step here, step. So this will make a step function generator. I will tell you what is step function right now. So, okay. And in for this example, we will use the integrator block to integrate the step function and see what's the output. So this is how you can put these blocks. And you will add one scope here because we have to see the output, what is output. So we have to include this scope also. So yeah. So before jumping into this, I will by Control R you can rotate these components like this. Okay. So if I run the simulation, if I run this simulation, so this is the graph of step function. Wait, wait. So this is graph of step function. So it is 0 to 1. It is 0 for just 1 second. And after that, it is 1 for rest of the time. So let's integrate this. And after that, we say this in this scope. So if you again press run button, you can see the integrated graph. Okay. So it's clear. It's clear till now how we how I'm doing this stuffs. Okay. So also I will tell you one more example, like you can include one sum block also. Sum block. Okay, how do I connect this? Okay, so let's, so here you can, if you click here, so this will open a arrow like this, a connecting wire. So this is how I connected like this. Is it clear? Drag the arrows, right. So for, so let's use this sum block also. So for next example, I am going to use two step functions and add them. Okay, so I will delete this for the time. So what I'm going to do is I will add two sum blocks like this and like this. I will add these two and then I integrate the output, like I search this integral part and I will integrate this sum output, and then we will see the output by scope. Okay, so this is our circuit. Before this, we can see the output also. Okay, we can see like how the graph will be. So it's 0 to 1 for 1 second. Oh, is 0 for 1 second, and it's 2 for the rest of the time. And if you see, okay, I think it's not like visible, change visible. So if you double click the step function, you can change the properties here. So let's say I put initial value to be 2 and then final value 0 for 1 second only. So the graph will look like this. Okay, it's 2 for 1 second and then 1 for rest of the time. So if I see the graph, so yeah, you can see the change right now. I think you can see. So this is y equals to 2x for 1 second and y equals to x for rest of the time. So is it clear till now how I'm doing this? Or if you have any doubt, you can ask in the chat also. The graph was not visible. Like, is it visible? Oh, okay, okay. My bad. Sorry. Wait. Okay, so sorry for the. So this is the graph. Like I sum the graph. So it is 2 for the first second and it is 1 for the rest of the time. So this is first graph, and after this graph, this is the second graph. So you can see this, the for the first second it is y equals to 2x, and then after it was like y equals to x graph. Okay, so I think it's clear now. Okay, so this is how this works. So yeah, this is some basic stuffs. So we have some time now. So I will tell you one more example about in Simulink, like you can make. Okay, so is it clear till now? You can raise your hand if it's clear. Okay, no problem. So our these basic things are done. So I will, you learn about the PID controller. Yes. So just wait a second. We'll learn about the PID controller. Yes, in the previous session. So we are going to simulate PID controller in our to in remaining time. Okay. Okay, so I will tell you like this is the equation. This is the equation, and I'm going to tell you like how we are simulating the PID controller. Okay. So the PID controller generally gives the force in the output. Okay. So let's take a PID block. This. So this PID controller will give force as an output. Okay. And and we will use one gain block as like like we are having force as an output. So I just divided by m. So we can get what acceleration from here. So like force goes from here to here, and then acceleration will come out. And after this, use the integrator block here to get so the acceleration we integrate it, so we get velocity. Okay. And if you further integrate it, we get position from here. So yeah, here from here we can get the position. Okay. So is this clear till now? Mm, okay. Okay, so after this, what we're going to do is we just see by the scope that what is the graph. So we are interested in position right now. So we will see position from here. Just wait a second. Uh, yeah. So we are going to see the position here. Okay. So here you can see this. Uh, uh, in our Newton laws equation, we put the acceleration and which is the input force times the spring force and that damper force. Okay. So we add a sum block here. We add a sum block here. Wait. Yeah. I add a sum block here. Okay. And then I put like three equations, one plus and two minus signs here. Wait. Huh. So the PID, the output will come in this plus sign. So I will tell you why. So as you see here, this is our total acceleration, which is minus b by this term velocity minus b times velocity by m, and this also. So by PID we get only this term, the input force, and we have to like give the full acceleration term. So we have to add one term here minus this one minus b times velocity because m is here only, m is dividing here only. So this is our velocity term. So we add a gain block here, this gain block, and we put it minus b, as you can see here, minus b times this velocity. Okay. And then we put it here. So from here velocity comes and minus b times velocity and it just add here. And then we add one more gain block and we put like, okay, so minus, so here minus term is there. So I don't have to put again one more minus. I can just put it like B. And for this, I put the K term here, K. So from here, I get position and multiplied by K and subtract it. So it's like minus Kx and then it's divided by M. So we get this term finally. Okay. So clear till now, or you are having any doubt? Okay, so I will take doubts afterwards because I have to end also. So okay, and so this is And like we have to set one more thing. So I will tell you this one block also. This is constant block. So this blocks in here, it will tell us like what is our desired state. So for the time I will take the desired state to be 1. Okay, like our block is at 0 and I have to take that from 0 to 1. Okay, and I will add one more sum block here, and I will tell, and I will put it like this. And so like here, this block gives the actual position which is right now here and our desired position to the PID, and the PID computes and give the force. This this force equation which it has to give input so that the block will come to this desired state. Okay. So you may be thinking like why this red warning is coming. So you have to go to MATLAB because we didn't define our variable. So like I put m is to 10, v is to 5, some random things, and k to be 10. And if I run this, yeah, you can see it here. Okay, so I didn't tune the PID controller right now. So if I tune it like this, so let's say again some random values. And so this is how this our PID controller works. So I didn't tune it perfectly right now. So that's why it's some weird graph. So yeah, so this is how we make our PID controller. Okay, so there is some more time, I think. So this is PID controller about, and okay, so due to shortage of time, like I in third week you will get to know about like LQR also. Okay, the LQR, how it works in MATLAB. Okay, so we will conclude today's lecture here. So thanks for your patience. Thanks for attending today's lecture. And if you have any questions regarding today's lecture, you can feel free to DM me. Okay, so yeah, thank you.